So within global circulation, we have three major categories that we're going to cover today. We have pressure bands, which are made up of polar high, subpolar low, subtropical high, equatorial low, subtropical high, subpolar low again, and polar high. You'll notice that a lot of these repeat, which we'll get into later. Next, we have convection cells. We have Hadley cell, Ferrel cell, and polar cell. And then we have global winds. We have the easterlies, the westerlies, the transwinds, the northeast transwinds, the southeast transwinds, the westerlies, and the easterlies once again. And finally, we will go over convergence, divergence, pressure gradient force, and my favorite, Coriolis force. So as you can see here, we have a visual model that we're going to use that is going to replicate the Earth. So before we get started, there's one thing that you all must know first, which is the highest installation at the equator leads to warm air rising, which in all causes low pressure. So with that being said, where do you think the warmest air lies on this visual map that we have drawn? That's right, in the middle at the equator. And if you would guess, what happens to warm air? That's right, it rises. So what happens when air rises off the equator? Well, it results in low pressure. So here at the zero marker band, that band is called the equatorial low. So I'm just going to draw a red L here just to signify low pressure. So as we're going to outline here, I want to ask you a question. When warm air rises and hits the top of that atmosphere, what is it going to do? Well, it's simple. It's going to do something called diverging, or as I like to call it, divergence. It's when that air comes back to hits the top of the atmosphere and ends up bouncing right back down. Now, once the air starts to travel, it's going to travel northwards and southwards, where it will eventually begin to cool down. As you can see here, it will roughly hit that cool down phase around, I would say, roughly the 30-degree mark. However, remember that this diagram of the planet is not tilted on its axis. So imagine as if the planet was facing you. So as you can see here, I'm going to put two blue H's. And that's because when that cold air comes back and hits the surface of our planet, it is going to be high pressure. This phenomenon occurs around the 30-degree marked line, where a stream of high pressure is going to be reflected due to the divergence. As you can see, this occurs at the subtropical highs. When this cool air reaches the surface, it is going to diverge again, which are illustrated by the two outward pointing arrows on the 60-degree line. So far, we have created a system that signifies a circulating pocket of air at the surface of our atmosphere. So I just noticed that where the subtropical high is, where we drew the two blue H's, need to actually be pointing inwards because of divergence. I'm not sure if I know how to fix that, just out of fear that we'll lose the whole lecture right here, but just know that between those 30-degree marks where the two blue H's lie, it's supposed to represent divergence, where the arrows need to be pointing inwards. So with this pocket of air that we have created, this circulation is going to represent something called Hadley cells. These Hadley cells are basically going to represent this circulation area that we have created between the 30-degree mark and the equator. Next, let's shift to the poles. As most of you can guess, the coldest air lies directly at the poles, or in this case, technically north and south. And when we have cold air, it sinks, creating once again high pressure. When cold air sinks, it likes to contract. Their weights take up much less space, and so they become more dense and eventually sink. This can happen if air particles move away from a source of heat. They might have risen very high or moved to an area that is over a colder shade. I like to think of like food as an example. If we have a hot cup of hot chocolate and we leave it out, you'll notice that when a cup is already hot, it cools off way faster than your cup that is already going to be cold. So with that being said, we have two zones here that are known as polar highs. So once cold air hits these poles, it seeks the nearest place for warm air. Hence, it cools off way faster. So let me ask you this. Where is the nearest zone of warm air? That's right, the equator. So as you can see here, we're going to draw two arrows at the 60-degree line, and this is going to represent that cold air moving away to the equator. This is called convergence. Convergence is essentially when horizontal winds cause a net flow of air into another region. As some of you may already know through previous labs and other exercises, convergence is something that we are very familiar with. This process occurs at the subpolar lows. Although the name itself is easy to remember, it is crucial for you to also remember that this is an example of cold air rising, which means that we now have once again low pressure zones. Although the polar is in the name, remember that this is the process of cold air moving to warmer air, which once again means that we're going to have low pressure looking too messy. I'm going to not draw the red lows, the low pressure zones for this one, but just instead we're going to move forward with the direction of the air in the subpolar lows. As the air converges, it will be forced to move upwards, given that the air is now in the process of heating up, therefore making it into the process of diverging. Now that we have created this spider web-like structure, we now have made up 4 additional cells. The cells located at the 60 and 90 degree zones are called polar cells, which, as you can tell, are very easy to remember, given that they're near the polar zones. And the other 2 remaining cells, located between the 60 degree mark and the 30 degree mark, are going to be called Ferrel cells. So now that we have covered polar cells, Ferrel cells, and Hadley cells, it is important that you realize that these 3 cells are, in our model, act as a tube, or as I like to call it, a blanket that covers the Earth. Now it is time for us to cover the 6 global winds. I'm going to erase most of the drawing that we have so far just to prevent a mess. So I highly recommend taking a screenshot for the next section and following along. We're going to follow the direction of the winds using the convection cells. They're going to act almost as our guidance. As you can see here with the arrows that I have drawn, wind blows from 90 degrees to 60 degrees, and then 30 degrees to 60 degrees in the same section as the Ferrel cell. And then all air meets at the equator, blowing from 30 degrees to 0 degrees, or since no one calls it 0 degrees, to the equator. Given that we need to take into account the rotation of the Earth, we must look at my favorite, the Coriolis effect. Now, if the Earth is rotating counterclockwise, things traveling towards the equator are going to flow right. And so if things are going to flow right at the top of the equator, then that means that the southern hemisphere wind is going to flow left. So starting at the top, near the North Pole, the first system is called the easterlies. This is fairly straightforward because the names of these winds are based primarily off the direction that they are going to flow in. Therefore, east is going to blow eastward. On the other hand, in the South Pole, winds are going to be also called the easterlies, solely because they originate from the east side. Although you may want to say that the winds here should flow westerly, that is not necessarily the case. Between the subtropical low and the subtropical high, the winds here are going to travel from the south to the north. Due to the Coriolis effect, they're going to travel to the right. Now these winds are going to be called the westerlies because they originate to the west, which can be shown here in the direction that they flow in. On the other hand, between the subtropical high and the subpolar low in the south, they however deflect to the left. As you can see here, there is a mirror that almost reflects between wind patterns in the north and the south. And now, just so you all can see it, I will label the subpolar low and subpolar high in the north and south with the prevailing westerlies. So last but not least, air flows from the subtropical high to the equatorial low in the direction to the right on the northern end of the hemisphere, and to the left in the southern hemisphere. You'll notice that they are both almost going in the same direction, which is different from what you would see on the other end of this diagram. Since we already have winds called easterlies, the names for these winds are called the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. Pretty simple and pretty straightforward. So finally, we are going to cover pressure gradient force. Pressure gradient force is simply identified in the direction that wind blows. In other words, air always flows from high pressure zones to low pressure zones. The pressure gradient force simply controls how fast wind moves. It can also be identified as the force that drives wind results. The gradient force, which is also known as the direction, tells us that when the gradient force is high, wind is going to move faster, and vice versa. Steep gradient produces fast winds, whereas shallow gradients are going to produce slower winds. However, when we're talking about gradient force, we have to talk about isobars, which are contours that connect places on Earth that have the same pressure. If isobars are closer together, the pressure gradient is going to be larger, whereas if the isobars are further away, the wind is going to be slower. Hello everyone, we have come to the end of the global circulation model. Thank you for watching, appreciate your time, and I hope to see you soon. Thank you.